Secondary tertiary, I think that's again 3 hours. Running times. Can you choose one of the for all 3 hours or not? And yes. And then for facility, it can be facility outside.
Okay, so I have the exam one from Dr. Young. Unfortunately, I wasn't able to get the QR code working and such. So I'll let you guys just go ahead and we'll have this posted on YouTube. So I'm gonna have this recorded. So please be mindful that your voice is gonna be recorded too. So go ahead and write down the these questions, and we'll get started with the exam review. This is exam one. Um, for that one? Yeah, so this recording we posted on our YouTube channel, the ACSUH. I will try my best to get a blank version and a key version as soon as I get this posted, okay? All right. Okay. So let me go and get started with nomenclature. So the first compound we're going with is Z2-iodo 1-methylthiobutyene. So what I've noticed is that we need to draw a structure of this material, and we have is an iodo. Oops, my bad. This is not color that I wanted. I'm gonna have is a iodo right here at carbon 2. We're gonna have is a methylthio, which is basically is a methane group with a thio group, which is a sulfur group, which is S. So I know I had to have some kind of I right here and also a methylthio, which means it's going to be a CH3S group. And then butene is my parent chain. So that means I'll have is a 4-carbon chain, 1, 2, 3, 4. And we're going to have a 2 on the double bond. Now, keep in mind that we also have a stereochemistry of Z, which means that they have to be on the same side. So I cannot draw it like this anymore. Instead, it's this right here. I would need to make it in this structure. That's the Z conformation. Okay. And at carbon 2, we're going to need to put a iodine right here. And then at carbon 1, we need to put a sulfur. So we're going to have to go ahead and do it like this, I believe. So butene, 2, 3, 4, 2 iodo, which means it's going to be over here. So I'm going to have my iodine right here. And then the 1, I'm going to label that as my 1 right here, just for clarifications. I need to put in methionine. So I need to basically put is this 1, a sulfur right here, and then there. Let oh, that must be yes, that must be a mistake. So let me erase that was the error that I was making. So this would look like this to make it a Z. So because on the same side, when you look at it on the right side, this is the top, and then this side would be at the bottom, but not makes sense at all. This talking about YouTube. So don't forget. Okay, that's what the structure looks like. And we're going to go and move on to our second molecule, which is a 1-phenoxybutane 1,3-diol. So in this structure, we have a phenoxy group, which means we're going to have some kind of benzene ring with an O. It's going to be on the first carbon. And then we're going to have a butane. So we're going to have 1, 2, 3, 4. That's our butane. And at the same time, we have is a diol, which is part of our parent chain. So at carbon 1 and at carbon 3, we should have is an alcohol group. So we're going to have an OH right here. And at carbon 3, we're going to have an alcohol right here. And that's about it. With a simple substituents, a parent chain with 2 alcohols, that is the structure. Okay. This third structure. It's gonna give this third structure just gives you the molecule, which now you have to find a way to name this whole thing. So there's two ways you can name this, but we're going to use the one that you guys are familiar with because there is a one that's much more advanced, but you guys will have to learn it in exam 3. So in exam 1 terminology, we're going to be doing a parent chain of cyclo, and then we're going to have two double bonds. So what I'm going to do is I'm going to put at carbon 1 right here. Do it right here. 1, 2, 3, 4, 5, 6, and 7. So that means my parent chain is going to be a cyclohepta 1,3 diene. Okay. Now the constituent is this CN group, and you might be familiar with this as the cyanide group or the C triple bond N group. We're going to be using the substituent name, which is cyano, which let me go ahead and spell that up. And it's at carbon 6. So 6 cyano, which is CYANO. And that is your only substituent that you have to worry about. So we're going to put them all together to put the whole nomenclatures. So it's going to be 6 cyano, then cyclohepta, 1, 3 buta. No, not buta. It's supposed to be just diene. My bad. This back right here. My bad. Diene. Okay, that's molecule 3. And then now our molecule 4. This one contains an epoxide. We have the structure right here, and it's a methyl group and a methoxy group. So what I'm going to do is I'm going to use the IUPAC naming. So where in IUPAC naming, we're going to be using the epoxy as part of our substituents instead of all of the other common names like oxyrane or oxide. So we're going to be using the IUPAC way. So at carbon 1, 2, 3, so we have is a parent chain of propane. At carbon 2 and carbon 3, that's where we describe our substituent of epoxy, which will be labeled as 2,3-epoxy. And then the other one, our carbon 3, also has a ether group or a methoxy group. So at carbon 3, I'm going to have a methoxy. And then don't forget stereochemistry. We do have stereochemistry because of the wedge and dashes. So let's look at these together. We have is a carbon right here that we have an oxygen, hydrogen. Let's put it right over here. A methyl group, and then this bond towards the other oxygens. So directly at it, we have a 1 right here. This is going to be a 4. And these carbons, we have 2 O's. So this is a 2, and this is a 3. So 1, 2, 4, 3. This is going to be counterclockwise, not because of the wedge. So that means at carbon 2, we're going to have a 2R. And now at carbon 3 right here, we go ahead and erase that one so it makes it much more easier to see. We have 2 oxygens that are directly connected to each other, but we do have a hydrogen that's just invisibly right here. Let's put that as a 4. So I'm going to as a hydrogen. And over here, we have it as a 3 because of the oxygens. So then between these two, we have is a, I believe it's a carbon, and that's it. Well, this one also has a carbon, so let's go and keep going. Carbon. This one has hydrogens, so this one's going to be a 1, and this is going to be a 2. So 1, 2, 3, 4. Where the 4 is on the dash, that's what we keep. So at carbon 3, I believe we're gonna have is 3s. I also did skip a step. I also forgot to skip a step, which I frankly forgot. Remember the rule of you want to have your substituents at the lowest numbers. That's what I did not do. So instead of 2,3 epoxy, it should have been a 1,2 epoxy, and also my stereochemistry should have a 1s instead of a 3s. So let me go ahead and put that away and erase this one. And then one more. And let's put this one here. Let's put this away. yes. Remember, you want the substituents, any substituents at the lowest numbers. Can I use trans instead of using R and S? Unfortunately, you can't in this situation, but based on the key. There is a way to label it, but um they are both Kairos, so I think a much more better description to that. Because you could have some of the system trans to be a Chiral at some point. Some point. Okay. So let's go ahead and rewrite this again. So it's 1,2 epoxy, and then this one's gonna be is 1 methoxy, and then 1 R, and this is a one, it's 2 R and 1 S. And now with the full nomenclature all together, we're gonna write this. We're gonna have 1 S, 2 R. You guys can see this. 1, 2 epoxy because of the alphabetical order. 1, 2 epoxy. 1 methoxy. Propane. Are we clear with all of the nomenclature thing? It's pretty much routine now that since from Orgo 1 that you're gonna expect to name compounds at least. Okay? Going straight in to reactions. I think everyone knows that everyone's freaking out about the reactions, or the first exam is going to be one of the most difficult ones because you have to bring in all of the reactions from Orgo 1 and then adding on top of Orgo 2, which is true. So let's go. So we're going to have to get our Orgo 1 brains warmed up and let's get working on these reactions. So looking from here, we have a blank as a reactant that we need to use sodium metal and CH3Br to form this compound. What reminds me about the CH3Br and the sodium chain is that there was a reaction that actually has dealt with these two together, and it's called Williams ether synthesis. You have dealt this in lab too if you guys are in lab. And so this means we have this coming from these two together. So all of this is going to keep together, but that one changes, deriving from that it was some kind of oxygen compound. So it's going to be this cyclopentane right here. That's a great John James. Right here. And then we're going to have our methyl group sticking out with the other two methyl groups coming out. But then over here, well, remember to get this Williams ether synthesis going, to get from something to ether, what was derived from this chain together was from an alcohol group. So we have an OH right here, and that makes sense because we have an alcohol group, we have a sodium metal that's going to take up the hydrogen to make an oxide, and then we could do a simple SN2 with the bromomethane to form the ether. Okay? Is there any other questions from that first reaction? Okay. Okay, that's okay. Okay, so reaction B. Reaction B we have is a para-substituted benzene reactant combined with sodium ethoxy. I think it's an ethyl thiol. There we go. In excess, and we're going to form a product with this compound. What that compound you probably don't know is a tosylate oxide sodium or sodium tosylate, and that means we're dealing with is an OTOS. So if you remember back in the exam 2 worlds, OTOS is basically one of our best leaving group things. So with combining with sodium ethyl thiol, that means it's a simple SN2 process. Now, to be fair though, as a note, it is on the benzene ring. It's sp2. It should not work, but ideologically, this is a theory-based class, so this could happen. So we're gonna have is a benzene ring with the methyl group right here. Oh, I'm sorry. Actually, no, I'm sorry. That's that's a complete mistake. That's a complete 180 mistake because the tosylate is part of the top. The tosylate is part of the leaving group. So my bad. This is probably this stuff right here. Oh wait, no, it is. Sorry, no, sorry for the confusion. Uh, this is what's supposed to be. My bad. it's a really good leaving group.
This is so.
Yeah, this is a sulfur, so so that's why it's called OTOS or tosylate. Uh-huh. So this whole thing on tosylate, it's a good leaving group. You could take it off with ethyl and it's gonna form a methyl S and then 1,2. That's it. That's literally what the simple SN2 exchange is. Um, Not necessarily. Oh, the phenyl is part of the tosylate, so that's why it's that's TSO. That's just it's just condensed. Yes. That's so that was that's how a tosylate would look like. So, oh, it's from here. Hmm? Okay. The benzene is part of the tosylate. So that benzene is actually over here. It's just condensed. We just only have the CH3. The whole thing OTOS is the good leading. Yes. I know it. Yes, it's actually an SN2 process. If you see a theoretically basis, the CH3 on its own is obviously going to go SN2, but the OTOS as a benzene ring and all itself shouldn't work as such. But it's just such a really good leaving group that could leave on its own. So that's why you can actually do this through SN2. Okay. Going on to reaction three. This one is a very convoluted one because there is a lot of things going on. We have is a alcohol and a bromine with something that's going to make this, then use magnesium and a ketone, and then use something else to form the same structure, but instead of bromine, we have is a tertiary alcohol. So it seems like in the middle step, we're going to be doing some kind of Grignard reagent. However, when we play with a Grignard reagent, we always have to avoid with the acidic hydrogen protons. And I believe Dr. Young have talked about this, that Dr. Beanhead taught you this. It's using the silo ether, isn't it? So we're going to be using the silo ether because it's a protecting group, as someone mentioned, that holds the alcohol group in place. And that was I think it was silo ether or tetramethyl silo ether. So it's TMSCl with pyridine or TEA. So I'm gonna write pyridine because it's pretty much recognized as one of the solvents like PCC and other things. So right, so pyridine, then it will hold on to the alcohol as OTMS. It's gonna react with the Grignard and the ketone to form that other side. And now we got to go ahead and just remove the protecting group. The protecting group that we had to remove was obviously the silyl ether, but the compound we had to need is some kind of acid to get rid of it. And one of the most common acids that people actually take off is the uh tert-butyl ammonium fluoride or TBAF. So you can write this like this, or you actually have to write the official way that the key says, which is NBU4F. So you can write this, the way I wrote this was TBAF because it's tert-butyl ammonium fluoride, or you write the actually NBU4F, one or the other. And it has to be in water. Okay? Any questions about the protecting group or we're good to go? Okay. So so we need to find a way to react this molecule without reacting the alcohol from this Grignard because acidic protons would react to Grignard pretty easily. So we need to do is going to hold off or protect the alcohol by using the silyl ether, which is what TMSCl stands for. It's a tetramethyl acylic silyl ether or silica chloride with the pyridine as our solvent that's going to protect or hold on the alcohol group into an ether group, which is OTMS. So then we're going to have to make the Grignard, which is NTBr, and then react with the ketone to form this entire structure. So we have finished the entire structure. Now we're just going to go ahead and turn it back into an alcohol group. And the way to do that is using some kind of acid, which is what TBAF is. TBAF, which is tert-butyl ammonium fluoride, that is what we can do to take off the silyl ether and turn it back into an alcohol group. So if the OH from product to reactant is like still the same the entirely, then it's probably a good sign that you might need to use some kind of protecting group. Okay? And that's a really good hint because you might need to use it for exam 3. We'll get that later. Okay. Reaction 4. Reaction 4 we have is a furan with a I believe it's going to be is a double bond with a 2 cyano groups and heat. This is actually one of the classic versions, not really the classic versions, but one of the hints of indicators that you're going to be using what's called Diels alter. And if you guys are an experiment, you guys had this experiment today, you probably already have an idea what it looks like, or you could experience it tomorrow, or whatever other days you guys have experiment days. But the idea is that what you're going to have is a diene right here with which is the furan, and then dienophile by the dicyano groups. So what I'm going to do is I'm actually going to go ahead and rearrange them into this because it's much easier to see how it's reacted. So I'm going to go ahead and put my diene right here with the furan like this, and then I'm going to go ahead and infuse with the cyano groups like this. And you can tell that if we trace something like this, you can see that that's where the Diels alter reaction is going to happen. Then by doing a concerted reaction, pushing this bond right here, then we're going to push this bond right here, and then this bond right here. I know it's hard to see. And so what's going to happen is there's a bunch of rules you have to play for the Diels alter for it to work very well. One of the things that you're going to have to lift it up of the oxygen. So instead of being flat on the ground for the double bond, it's going to be lifted up from the reaction. And at the same time, due to the fact that there's a double bond still remaining from the Diels alter reaction, the cyano groups must be in the bottom, which is called the endo rule, because it wants to actually line up with the molecular orbitals. Okay? So then it's going to go ahead and it's going to form this really cool bicyclic structure, which if you like to try to attempt to draw it, go for it. So it's going to look something like this. And I'm going to do is point this O up and then down right here, which I know it's hard to write. Actually, let me actually go ahead and erase this to make it much more clear. Oops. Yes, if you're doing a wedge and dash configuration or looking at the top or you're doing like a flat view of it, you want to make sure you put your endo rule by having dashes first. So it's gonna look like this. It's gonna look something like this. Okay, and then I'm gonna have my cyano groups right here, and then my double bond right here. Now, if you're doing the flat version, which I'll draw it on the side to make sure it looks clear. It's going to be the cyclohexane as usual. I'm gonna have my double bond right here. I'm going to put my wedges right in the middle. So this is an alternative way you can actually draw it too, and that's still acceptable. And then I'm going to have to put my dashes, as someone clarified, for the endo rule, CNs. So you can write this as a bicyclic three-dimensional way. This is the one I drew in the box, or you can draw this on the top view as top and flat view way. Those are acceptable options to answer. It's actually happening at the same time. So the diene and dienophile are breaking and forming bonds at the same time. This is what's called a concerted reaction. So you see that it's happening at the same time. So it's just rearranging all of their pi bonds into new sigma bonds in the Diels alter, while holding one, pushing back to be that alkene. No, dienophile is just it's kind of like the electrophile of the diene. That's the way to describe it. But yeah. Oh, the end over means that the withdrawing groups contain pi bonds, and it wants to be connected under the diene of the product. So you see that the cyano group right here, this is a C1N. What it likes to do is that it wants to be lining up its orbitals underneath with the double bond right here. So that's why it focuses on this endo rule. While many people say that the exo product, which is the one that faces upwards, doesn't work because it gets too far away from it to um, to be arranged. So that's why people like to call it the ender rule. It's because it's that underneathness of being next to the orbitals. Okay, moving on into reaction five. So reaction five, this is a ether group with an excess acid or hydrobromic acid. So what's going to do is we're going to have to break down this ether into its components. And what better way to see that really easily is look at the side that has the benzene ring. It's not easy for it to break it down because like SN2 and sp2, you cannot find a way to force it to get off of the benzene ring easily. So that means that when we react this together, we're going to have is actually a phenol. So my benzene with alcohol group, so that is right here. Plus, because we remove the alcohol, we're gonna have to have the bromine on the other side. So it's gonna be a tert butyl methyl. Bromo you, you you know what I mean. Uh it's basically dimethyl there we go. Bromo dimethyl ethane. There we go. I don't know, that was hard. That was hard to say. Or you can say it another way else. One bromo, one methyl propane. There we go. Okay. The next one, this one's actually a very interesting problem. Has two double bonds, and what's going to do is an intermolecular 2+2 cycle addition. So it basically is like a special addition of the Diels-Alder. It's not actually Diels-Alder because Diels-Alder is a 4+2 cycle addition. A 2+2 cycle addition is another version of what they call the paracyclic reactions. You're not going to be dealing with a lot of paracyclic reactions throughout this entire course, only the Diels-Alder. But if you've ever been curious about other reactions like this one, the honors version of the Orgo 2 is doing this, and it's going to be doing all that 2+2s and then the other rearrangements of the paracyclic reactions, like the electrocytic ring openings and the symmetropic rearrangements. But for now, we're just going to just go straight in and say, what the heck does this work? So what's going to happen is that I'm going to be rearranging this to where these two are close together. In other words, I'm going to have to find a way to make them close together for it to react. And what's going to look like, and it's going to be a little difficult to see, is that it's going to have this pentagon right here with the square next to it and a hexagon right next to it on top. So it's going to be a pentagon that's bonded to the side of a square, then bonded on top of that with a hexagon. I know it sounds just really weird, but trust me, try it with a model kit and try to bend around to get that hexagon, and you're able to get that square from this cycle addition. Yes. Yes, that's correct. Um, I think it isn't that 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 would probably requires an additional high bond somewhere. It would have to require some. Mhm. Okay. Um, let's go on to the next reaction. The next reaction is a it's an ether with a bromine and a CH3OH and heat. So we want to mind that there's also a label that says low temperature and high temperature. This is the one involving with temperature dependent and products. So this is the stuff that you guys heard about things like kinetic product and thermodynamic product. This is where it matters. So looking at this closely, we have is a alcohol with heat and a bromine next to it. So it's going to be treated as more of an SN1 reaction that it's going to replace the bromine to form a carbocation, and then it's going to do a substitution through solvolysis, and that's going to form as a simple SN1 product. So it's going to be just this. So that's the low temperature one. And then the high temperature one, well, once we have the bromine as a leaving group, because remember, if we're treating it as someone that's going to S1 process, the high temperature is going to force the alkene to rearrange through resonance because it's much more stable in terms of an alkene. So if you look at the alkene to this one, it's bonded to two different places. But now with resonance, so because we actually took it as an intermediate, so let me draw this right over here. I can actually find a way to rearrange this double bond over here because of that extra energy for it to be much more stable. So with resonance, I'm going to go ahead and put this right over here. And now this one gains the bond and the other one loses the bond. That means the carbocation is right over here. So that means that's where the high temperature one or the thermal product is gonna have bonded to instead. So I'm gonna go ahead and put that over here. Double bond, then this. That would be the product. Are there any other reaction questions? Could it do a ring opening? I don't think so because yes, there is a double bond there is a carbocation right here, but the best way to actually open the ring is you would have to have some kind of like acid to like break it down or something. But in this case, we don't technically have that acid. We just only have is that double bond to rearrange the resonance, so it wouldn't be possible to open the ring. Remember, this is in terms of thermo. When we talk about the carbocation, that's more of a kinetic. So thermo is in more energy. So I want to have the highest energy possible to be the most stable. I think that's when many people have been so confused in some of the thermal products and the kinetic products that one involves speed, so that what's more stable in terms of the charge, versus which one is more stable in terms of its energy. That's a thermo. So that's why in high temperatures, we focus is the thermal product, which is the alkene to be the most stable, which is a trisub, versus a low temperature, which is the fastest way to make the carbocation, which is the charge on over here, which is the kinetic product. Okay. All right, so we're moving on to the mechanism questions. There is actually two different mechanisms that we're going to pop in, and we need to answer one of them. We're going to be answering the first one, and only the first one. If you guys are curious on the working on the second mechanisms, we'll be doing that off stream. So I'm going to do it offline. So we're going to focus on mechanism one, and it requires is a bromium alcohol with sodium hydride, and then a a phenol group with an H plus. So it's going to be some kind of acid phenol. Okay. So a BROH, this is probably being some kind of halohydrin formation, and we're going to use a sodium hydride. And what that means is that I'm going to be actually doing is we're going to have this hydride come in. So it's going to be H minus. It's going to be part of grabbing the hydrogen proton to be hydrogen gas. So it's going to grab that, and it's going to have the bond go back to a lone pair. Okay? So this is going to form. No. Sodium hydride. So it's an H minus. It's going to grab a hydrogen proton H plus to form hydrogen gas. Sodium is just a solid ion that's just going to float around the solution. So it's going to be act as like a spectator ion. Sodium metal on its own, yes, it will grab the hydrogen proton on itself to be a hydride ion, to be an O minus. But since we have hydride ion, that's much more reactive than the sodium metal. Mhm. Okay, so it's going to form this. So what's going to happen is that it's actually one of the alternate ways to form the epoxide. So traditionally in Orgo 1, we usually do is the MCPBA from an alkene. We can actually do an epoxide by doing halohydrin formation and then use some kind of hydride to form the epoxide. So that means the lone pair right here is going to go over here, while at the same time the bromine leaves as a leaving group. So that's going to form the epoxide like this. Okay. Now, that's the first step. So this is just the first step. So that's done. Now we got to do the second step, which is a phenol with an acid. So I'm going to start off with an acid because it's an acid catalyzed reaction. So I'm going to grab the O with the H plus. So I now have this. And we have a phenol group. So pH, then an OH. And with epoxides doing with an acid catalyzed reaction or a base catalyzed reaction, this is where that asymmetric creep matters the same. So if you heard the phrase BLAM, base least attacks most, this would help you in terms of determining what the material is going to attack um, after adding a base or an acid. And since we're dealing with an acid-base epoxide opening, that means we got to put our group, the phenol group, on the most substituted side. So the most substituted side is this tricep right here. So this alcohol group is going to grab it right here, while at the same time, because it's five bonds, it's going to break it up into over an alcohol group on the other side, forming this molecule over here. Well, maybe not directly, because I did forgot one more step. It's actually OH because it's not only it has to be it's not the entire thing. We need to do grab the hydrogen proton. So I'm gonna use water because it's just an acid catalyzed, so it could be H3O plus. So I'm just using it as like an after use or like a side as a byproduct of it. Push that to get the hydrogen proton, and then push it back as a lone pair for the oxygen. Then this would form the final product. Okay. Remember H plus it could be any form of acid. I just arbitrarily just chose H3O plus and then turn it into H2O because we already used it over here. And then this just as a byproduct just sitting around, and then they come back to use to go back to regenerate as a catalyst. Hmm? Should we use the NaH deprotonate this? No, no, because remember, we already have because it's already been used up on the first step. This is from the second step, so we have to use the already used up catalyst to regenerate it. Okay. Okay. How do you know that? How do you know this is a ring? Um, because of the hydrogen ion is going to grab the hydrogen proton, so it's going to be an O minus, and this bromine, like all the alkyl halides we have done before, it's going to form it's going to form a hot spot or electrophile on this spot. So with a nucleophile next to the electrophile, it's going to be easy for it to form that oxide. Wait. It's an acid. It's because of the H plus. That's the strategy when it comes to attaching the pH OH to any other group after adding the base or the acid. So BLAM stands for base, least, acid, most. So what does that mean is that if I add a base catalyst, then I'm gonna put my group onto the least substituted epoxide side. So let's go back to this one right here. If I were to add like a base instead, so let's say it was an O, let's say it's water with an OH minus, then what's gonna happen is I'm actually gonna do is grab this here first, open this up, so it's gonna be on the other side, and then I'll be deprotonating the water. It's gonna turn back into a base catalyst again. Because remember, we had to regenerate for catalyst work. The AM stands for acid most. So that means I'm gonna protonate first by putting an acid. And then afterwards, whatever group I have that's part of the acid catalyzed reaction is going to attach on the most substituted side of the epoxide, which in this case, what we draw from here is the most substituted because there's three subs over the other side, which only has two. So it's going to attack over here, open it up, and that will form our intermediate to grab the depronation to regenerate the acid catalyst. Okay. Are we good with mechanisms for this one? Okay. Let's move on to the next question. We need to devise a synthesis questions. Everyone should love synthesis, right? No? Just me? Okay. So we have a choice between either the top one or the bottom one. I'm actually going to go ahead and do both synthesis because I think everyone should have a lot more practice on trying the synthesis. So we're going to do both. And so the first one we have here is we have a cyclopentadiene. We're going to use any reagents and multi-steps to form a bicyclic compound with two alcohols, anti to each other. Okay, so what I do know when it comes to cyclopentadiene and forming this bicyclic compounds, I need some kind of molecule that would actually form that bicyclic at first. So what really spot in my head is to use some kind of which is already reviewed. My bad. Is to get some kind of dienophile, which is just basically it's just an ethene. This would be able to do with a Diels-Alder reaction, so it's going to form this bicyclic compound. You can put heat because that would actually indicates it, and you need to put a double bond right here. Now you can also put it on the other side, but remember they're symmetrical, so that you can just reflect them and such. And then next. That's our end goal. We can't there isn't a way to just directly get from this to this, so we have to take it step by step to build the molecule. That's the idea of the synthesis. Okay, so with the diene and dienophone from a Diels-Alder reaction, we form this bicyclic compound with an alkene on the side. So then now what's next? Well, I'm going to use MCPBA. And follow me through. Yes, there is two different ways you can do this, but I think because it's symmetrical, it should be realizable that it doesn't matter. So I'm gonna go ahead and build my molecule again. Okay, potassium permanganate. No. The reason why you cannot use that one is because it's gonna form a syn addition. It's gonna form a syn diol, which means same side alcohols. We want anti opposite sides. So I have to do the ring opening of the epoxide and then add an acid to form that anti-addition. So I'm going to use the MCPBA to form the epoxide and then H3O plus to open the ring at anti-directions. That's where you get the anti-addition of the alcohols. And that's where my synthesis ends. Okay. Water. The problem with that is that I will have only one alcohol. I need two alcohols. Okay. Let me go ahead and put a little more zoomed in up here. So I'm going to go and move on to the second one. The second synthesis is a cyclopentadiene, now this time with a 2-carbon group and an alcohol group. So for this, I'm actually going to start off backwards. I'm actually going to start off backwards because people like it forward because they have the starting material. I like to go backwards because I know where it derives from. That's just my opinion. So I'm actually going to do is start off from this, and I notice that there's a 2-carbon iron alcohol, and I need to get back to this. So I know I need to break this down apart. And since we talked about things like ethers and epoxides and all of these stuff, I noticed that this is a 2 carbons and an alcohol signals that this has to be coming from an epoxide. So that means this is derived from an epoxide and then a water molecule. Because, and this is where the it came from. If we have an epoxide and water, that means it came from a base. It's coming from something basic. It's something that was basic that I can think about. That's really interesting. Is it Grignard? Yes. You heard me. You heard me. Grignard is actually a basic compound. So then now I got to go ahead and deconstruct it from the Grignard. As I said many times from exam 3, Orgo 1, Grignard all the way down. I'm going to use Grignard with ether. to form the bromine. And then going back from this, because there's alkenes, this is a lytic position, that means I'm going to use this. I'm going to be using NVS in light. Is that it? Yeah, magnesium and ether. I probably should rate this more experimentally. Magnesium and THF because you guys dealt with THF before. Tetrahydrofuran. It's an alternative to the solvent of ET2O. So remember, grignard is a basic compound, and so when when it's going to attack the epoxide, since it's symmetrical, it wouldn't matter which side it attacks, but it will open the ring to be an oxide, and then the water molecule it's going to be protonated, so it's going to regenerate the base catalyst. It's going to regenerate the base. An alkene reaction, that's possible. How do you test the cyclopentadiene? Mhm. Because when you open the epoxide, it's going to be an O minus, so you need to protonate with water to get a base. Because remember, Grignard on its own is a basic compound, so it's going to attack the epoxide to form an O minus. So with water, it's going to regenerate the condition to be a base. But instead of being the Grignard, it's going to be the OH minus. For for the exam, do not draw the intermediates. It's only for mechanism questions, but for the sake of just freshening what it looks like, sure. So I'm just gonna say this is equivalent to this. Yeah, this is a minus charge. And I'm gonna use my here's my epoxide. So here it is. This is gonna attack. And the water molecule. This is a terrible arrow. That's like the mechanism that translates from this step to this. Make sense? Yeah, it acts like yeah, Grignard is like a base. Hmm. Okay, is there any more synthesis questions? We're good to go to the next one. This one's actually a very fun one. Back in Gen Chem, you guys dealt with something called phenolphthalein. So it turns white and then it turns red. This is the molecule of phenolphthalein. This is an acid-base indicator that it drops colorless when it's acidic, when it's gonna turn red when it's basic. So this is the molecule. So what we're doing is assuming there's no degenerate orbitals, we're trying to figure out how many nodes are there in the highest occupied molecular orbital, or what's called HOMO, or how many nodes are in this lowest unoccupied molecular orbital, or what's called LUMO. So how can I calculate how many nodes that is the highest occupied and number of nodes on the lowest unoccupied? Well, just to get an idea what they are, HOMOs are usually one less node than the LUMO because that's basically the electrons that occupy the pi bonds. That's gonna that's gonna characterize as HOMO or LUMO. So I'm gonna give you a simple demonstration of what a HOMO and LUMO looks like by using butadiene. So I have this molecule right here, and pi bonds contains 2 electrons per each pi bond each. So I have this total of 4 electrons involved in the bondings and anti-bondings of the molecular orbital. So remember the ideas of bonding and anti-bonding back in the Gen Chem days. It's like probably like almost like a year and a half ago. So it's gonna form orientations of these molecular orbitals to form these bondings and antibonding configurations. And so one way I could do this is do a all in phase to each other. So that's like our most bonded energy component, and this one has 0 nodes. And then we get to the next one where we need to have 1 node. So I had to have bonding over here, but then I got to have some kind of anti-bonding in between to form that single node. So that means I would have to do something like this instead. That will form that node right here. To make 2 nodes, you have to alternate two. You had to alternate 2 in between. So you can see there's a node right here, and then a node right here. And then lastly, let's just alter configurations. That's gonna form the most anti-bonding or the most highest energy possible. And each of them can occupy at least 2 electrons. So again, this is a simplified demonstration. Then we'll come back to the actual thing with phenolphthalein. So with 4 electrons occupied in this butadiene, I need to fill it up like this. And so what's telling me in this molecule is that my HOMO, highest occupied molecular orbital, is at 1 node. So this is my HOMO. While lowest unoccupied molecular orbital is the one above it, which is 2 nodes. So that's going to be my LUMO. There, that's like a simple demonstration. Now we got to do is actually form the more complicated version with phenolphthalein. And my strategy is count your double bonds. Count how many double bonds are involved with the phenolphthalein when it's red, because it's asking us when it's above 8. Okay, so we're talking about this molecule right here, and we need to count all of its double bonds that's occupied. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So we have a total of 22 electrons that's going to be involved in the molecular orbitals. However, using the simple demonstration way I just did right here, we know that two electrons are occupying with 0 nodes. So we have 2 at 0, 2 at 1, 2 at 2, 2 at 3, and so on and so forth. So a strategy that I use is we're going to divide it by 2 to make 11, plus subtract 1 because there is one bonding orbital with no nodes. And that will tell me how many nodes are part of how many nodes is the HOMO, while the one without it is the LUMO. So that means number of nodes in the HOMO, there's a total of 10 nodes in the HOMO, while in the number of nodes in LUMO, it's 11. Again, if you're still a little bit like flustered, like how I got those numbers, try drawing a total of 22 molecular orbitals, and that will explain pretty much every way as possible that there's that many nodes, and that's the highest you can go up to, and the lowest you could be unoccupied such. Okay. Remember, pi bonds has 2 electrons. What if it's part of the conjugation? That means it's part of the molecular orbital conjugation system. So I'm going to count so I'm counting every single pi bond that's involved with the conjugation. And with phenolphthalein, there's a lot of conjugation happening all around the place. So that's why I'm counting the carbonyls oxygen, because it's part of the conjugation system. Okay. This one. So you see right here, this is also bonded to the double bonds right here. So the conjugation means that they have to be sp2 altogether. So you see that one over here, I can move this bond right here, and then I can move this bond right here, here, and here. So it's just moving around. It's basically just moving around everywhere with the conjugation system. Okay. All right. So then the second part is asking us is explain briefly why the first structure is colorless and the second structure is colored. So it's basically telling us how is it possible for the same molecule to be colorless while the other one, when we actually put it on a basic condition, makes it colored. The reason why is because that when we actually how do I say did the conjugation of the energy system with 0 to 20, I think it was 22, 21 nodes, I believe. The energy difference going from 0 to 1 node is a huge. So going from the one at molecule at the one on one side, this one means that we can only see it clear because the energy that actually releases this conjugation system is something beyond the visible light spectrum, which means they're releasing ultraviolet radiation, quote unquote. While the conjugation that's on the other side, where we actually have it as the nodes of the LUMO, this one is the energy difference is super close enough where it's actually spewing a color in the visible light spectrum. So the idea is that the difference in the HOMO and LUMO energy what causing it to be um, one side to be colorless is because it's spewing a different EM EM waves, while the other side spews some kind of colored EM wave because the energy difference is much closer. So yeah, the larger the energy gap is, that means you're gonna have a smaller wavelength. That means you're gonna be spewing like more towards the gamma ray side. While if you have a much closer energy difference, like within like maybe like within between 400 to 600 nanometers, then you're spewing in the visible light spectrum. So the more energy you have spewed, that means you're going to spew something more towards the ultraviolet side. Well, the more closer the energy difference they are, as in like it's the delta E is closer to zero, the more closer you are going towards like the visible spectrum or infrared light. So um how can I tell? How can I tell? When it comes to the HOMO lumos of the colorless and the colored version. So if I did this one over here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. These are all part of the conjugate system, but they aren't. Why they aren't? See this sp3 right here? So that means I can only stack up to um about 5 nodes. 5 nodes. That means the gap between node 3 and node 4, which is the HOMO and LUMO of a benzene ring, is too large. It's too large. So that means it's going to spew an ultraviolet. It's going to spew an ultraviolet observation. So you're going to spew some kind of ultraviolet spectrum if you have UV eyes detections. But with the other system over here, with a total of 22 electrons, the conjugated system of our HOMO and LUMO at 10 and 11 is much smaller than a HOMO and LUMO of 3 and 4 nodes. Okay. So the higher the HOMO and LUMO is in terms of nodes, the energy difference or delta E decreases, so it's going to skew more towards the visible light spectrum over a huge difference, so a high delta E, making it more skewed towards the ultraviolet spectrum. Okay. And finally, we are down to our second to last problem. This is the spectroscopy problem. So everyone loves our spectroscopy, I'm pretty sure, I hope. We have a compound of C9H12O2. We have a proton decoupled spectrum on the following page. And we also have something happening with PCC, or pyridinium chlorochromate. And that means we're going to have a new signal appearing at the 9.7 ppm of the proton and at 200 ppm on the carbon-13 NMR. And we're going to have to identify this compound. So C9H12O2, when reacting with PCC, that means when we detect it again through NMR, we have an additional peak around 9.7. Okay. So I'll use that information later because that indicates something. But the C9H12O2, let's use our unsaturated numbers. 2C plus 2 minus H over 2. So that means it's going to be 20 minus 12 over 2. So that means my unsettled number is 4. And typically when you see 4, you're going to have to do something with benzene rings. So definitely it's got to be something with benzene rings. We also have 2 oxygens. So this could be mostly going to be some kind of like alcohol or some kind of ether group. Let's check. Let's go ahead and check around the this compound right here. So what we have here is a 3-agent doublet, which means that we have a CH3 next to a CH2, and it's only that. Then we have a 1H sextet and a 2-agent doublet. Let's start off with a 2H with a CH2. Oh, sorry, it is a C. If it were to be a CH2, it has to be a triplet. There we go. My bad. Okay. So a CH2 next to a doublet. This is where it gets the CH. There we go. That's better. And then at the same time, this 1H and sextet, that means it's next to a combination. It's next to a combination of a CH3 and a CH2. So that's the CH next to a CH2 and a CH3. One thing to note about this is that this is beyond or more downfield. Which means more to the left of the peaks of the 2 ppm. It's around nearly 4 ppm, which means that these two bands together have some form of electronegativity pull or something bonded next to bonded to it, causing that downfield. So that means there's going to be some kind of oxygen bonded to them. Okay. Then when the 1H singlet, which is between 2 and 5, we have is an alkyl alcohol. It's an OH. And then this whole thing altogether, I know it's all somehow a bit separate, but I'll explain the molecule, the reasoning why and such, is technically they're all around about 7 ppm, meaning that overall the whole picture of it means it's some kind of monosub benzene ring. So it's going to be a benzene, it's going to be a monosub. Okay? So then the other information also should mention that we have is at 9.7 ppm, which means that if we detect this product with a 9.7 ppm, this ppm is describing is known as the aldehyde peak. So this aldehyde peak is usually between 9 and 10, and that means that our reactant that came from that is coming from a primary alcohol would react with a PCC. Because if we did it with a secondary alcohol, it would form a ketone, which would not detect that high. It would detect around 2.1 or 2.2 ppm. Yes, you will given an IR, NMR, and carbon-13 NMR reference. Let me go ahead and pull that up below. That's the information you will get. So here's your IR right here, your proton NMRs, and then your carbon-13 NMR. So again, if people say that Orgo to Dr. Young's materials, it's basically a similar format as Dr. Low H dose is reference tables. Okay. So monosub we have is an alcohol group. That's going to be primary. So the best one that's going to be primary is probably going to be this has to be this one. So we're going to have the alcohol right here. And that means this one over here is going to be a standalone oxygen. Okay. The reason why is because this alcohol will be secondary. It wouldn't be a primary alcohol because it forms the aldehyde from that PCC. What was yours? The chemical formula? The chemical formula is C9H12O2. Okay. Okay. So we have a monosub, an primary alcohol, this whole thing, which means that we're going to have them all together like this. We're going to have a benzene ring that's monosub, ether, then we have that methyl group CH3, a CH2, and then an alcohol. That will be our molecule. Okay. Is there any questions about the spectroscopy? Which one? This one? To the ring itself. So let's look back to this. So remember we said it's a primary alcohol because of that PCC evidence. So that means that it has to be next to the CH2 and CH. If it were to be over here instead, it's going to be a secondary alcohol, which would contradict PCC evidence. And the reason why this is not connected to the ring is because that will form a cation charge. We want the molecule to be as most neutral as possible. So that's why it looks best connected when this oxygen is next to the ring, and then we have the CH2 next to that CH. That means that means it's on the other side. That means when we overlap it, we're gonna have this alcohol technically over here, and that one matches this description from this to this when we overlap it. Does that make sense? Okay. Hydrogen around the benzene. So the reason, it's because it's around that 7 ppm. So around that 7 ppm, that's where all the benzene or aromatic rings show up in the uh in the ben in the molecule. So all the hydrogen protons that are involved in the benzene ring is usually around that area, around that 7. And then altogether, since there's 5 of them around that 7 ppm, that means it's going to show up as 5 distinct. There's 5 hydrogen protons around that aromatic ring, which means that it's going to be some kind of monosub benzene ring. Sorry, that sounds confusing. So, like the overall picture of the 2H, 2H, and the 1H over here is saying that around that area, there's 5 hydrogens on the benzene ring, which makes it a monosubstituted benzene. Yes, because yeah, you can say that because it's around that 7 ppm range, which around that 7 to 8 ppm range are usually the aromatic hydrogen region. But other ones you should be aware of, the para-substituted benzene ring. This is where you have that doublet split on that 7H1. And and there's other ones you should probably notice. You probably should notice some kind of like meta one or some kind of ortho one, but that's something that you will learn in the exam 2 and the final exam sooner or later. So that is the structure, remember? The benzene, O, the CH, CH3, CH2, and the OH. But we're actually not done yet. This is the second to last question. We have some ACS questions that will be popping in here and there. So some ACS questions, you guys need to know it for the final exam, so you should probably be comfortable to be familiar with these kind of questions. These are just multiple choice, but I just erased the multiple choices because let's go ahead and figure out some evidence of how to answer them without them. So looking at these particular 4 questions, let's start with number 1. We need to figure out how many signals from how many sets of protons will be observed in this proton NMR from this compound. So we're just trying to figure out how many distinct signals we can pop out from this molecule. So let me go ahead and draw this out. I'm going to draw this. There's hydrogen right here, hydrogen right here, hydrogen right here, hydrogen right here. And what we can see from there is that this is parasub. So that means we're going to have some kind of equivalencies, which means we're going to have duplicates and count it only as 1. So that means we're going to have 1 right here and then 2 right here. So we're going to have 2 signals from the benzene ring. Moving on to the next ones, we have is a third one that's next to the oxygen right here, a fourth one that's next to the aromatic ring, a fifth one, and a sixth one, and a sixth. Why these CH3s over here are actually 2 distinct things. The reason why is because since that oxygen has a direct pole of it, it has a little bit of subtle influence on the other CH3, causing it to be slightly more downfield than the other one that does not have the oxygen atom. So that's why there's actually 6 distinct signals for this molecule. Okay. Because you see that oxygen atom right over here, so this one will be different than this one. No, that is a carbon, I believe. Let me erase this. Yes. Uh, okay. I think that's much more clear. Okay. The second part is what resonance structure would contribute to the most overall picture of this molecule. In other words, we need to find the major contributor of this molecule. And the idea to do this is we need to figure out what are other arrangements we can do to get the full octet and at the same time fulfill the charges that they are better suited. So we have all of this. And what I can do is I could put this bond back over here. Or actually, no, let me actually switch this up a bit. I'm actually going to put the bond back at the oxygen, O minus, and since that will cause a C plus, I could put it over here so that we have is a O, C, N, and CH3. So that's O minus, C, N plus, CH3. That's one way. Another way is basically put them back like this. So let me go ahead and try that. Actually, let me check on something. Another option I could do is move it to a single one like this, and then we can do something like that. So we could do something like O triple bond C, which is now a plus, and then we have a C and with a minus charge and a CH3. And then other ones I can also do is let me see what other ones they have posted. I can do them as just as individual stuff. So I can have like O minus C plus 1N CH3. But again, our goal overall is we want to make sure that these two rules fulfill for the major contributors. Octet rule, and then afterwards, if octet rule is tied, what formal charge is better suited for these atoms? So obviously from this third one, it does not work because we have a carbocation, and as a big golden rule about octet rules, carbocations never satisfies octet rules. And then the other two right here, they both all satisfy the octet rules because the CH3, the nitrogen has 4 bonds, the carbon has 4 bonds, and the oxygen has 4 bonds, quote unquote, because 3 lone pairs in the bond. Now we should figure out is which arrangement is actually preferable to sit on in terms of their formal charge. And if are you given to the periodic table, yes, on the ACS exam, you will have a periodic table regardless. So there's periodic table right there or over there that we have as an oxygen and a nitrogen shown in the periodic table, and the oxygen is a higher electronegativity, making it preferred to have the minus charge over the positive charge. So that means we're going to take this resonance structure as our major contributor. One more time. This way? No, because it's already 4 bonds. Okay. The third part is which is the order of fastest to slowest for the rates of an SN2 reaction of these alkyl bromides with methyl and DMSO. So basically, we're trying to figure out which one is the fastest way as possible to react this alkyl halides with this nucleophile in DMSO. So if we remember our trends and the structures of it, primaries or methyl groups are much more better than the primaries, and then the secondaries, and then the tertiaries. Other ones we can think about this that would actually make it much more faster is if we have a much higher nucleophilicity. Since it's just CH3S minus, we can only do is change the structure from these alkyl halides. So looking at this, our bromine right here, a bromine right here, and our bromine right here, we have is a primary, we have a secondary right here, and then we have a tertiary. Okay. With SN2, we want methyl, then primary, then secondary, and never tertiary. So that means we want 1 as our lowest. Then between these two, we're going to have 3 and then 2. Now, 2 is a big indicator to add to because we have the primary group and it's allylic. So it has more places to react altogether. But that wouldn't be the case because SN2 just is a one-step reaction. It's going to just switch with stereochemistry and it only happens on one side. The only thing that has that resonance structure is that SN1 reaction that would make much more faster and such. So, but it still is a primary alkyl halide, so it still will be one of the fastest SN2 reactions than the chair conformation, which is number 3, and then the bicyclic one, which is 1. That's from fastest to slowest. Okay. And then finally, which two compounds ionize the loss of bromine ions to form the same carbocation? Okay, so if we ionize it with the loss of the bromine ion, so we take this off right here. Okay. Which two compounds, so we have to find two compounds are basically the same carbocation exchange. So if we look at this one right here, we have a positive charge right here. So it's basically is a vinyl carbocation. The same thing goes with this one right here. It's a vinyl carbocation, which it's not possible because having a nucleophile with an electrophile charge just kind of makes it very unstable. Kind of like that triple bond intermediate that we talked about this in Formula 1. So 2 and 3 just isn't possible. But with 1 and 4, if we have a carbocation right here and a carbocation right over here, through resonance structures, they're basically about the exact same thing. So with resonance structures, these are related. If you can see well. So you see that bonds right here and the positive charge right here. That matches with this one if we switch it over here to have the bond right here and the carbocation right over here. They look exactly the same. So that's what makes these are the same carbocations, meaning that I should have circled, because it's multiple choice, something involving with 1 and 4. They're the same carbocations. No, because remember, it's a nucleophile with the electron density from the double bond. At the same time, how they get a formal charge, holding the carbocation charge. So it's a vinyl nucleophile carbocation electrophile. So that's why it's kind of contradicting, and that we cannot find a way to move that lone pair, the double bond and such. Okay, and so that is the end of the exam one. Hoping you guys actually learned something and review everything you have had. You're free to go, and I'll have this posted, the blank and key version of it. If you guys have any questions, to stand by to further your knowledge. Okay, and without further ado, that is the end of the exam one review. So good luck on the exam, you guys, and I'll see you guys again.